Hi everyone, I hope you're okay. This is the 8th video as promised. Uh yeah, let's jump into it, guys. Let's jump into it. We are told that two acids HX and HY of equal concentrations are compared. The pH of HX is 2.7 and the pH of HY is 0.7. First question, we are asked to define an acid in terms of the Lowry-Bronsted theory. An acid is simply a substance that ionizes in a solution to form a higher concentration of hydronium ions. Ooh, what's a Bronsted-Lowry? Okay, guys, that was the definition for Arrhenius theory. Ne? Just say an acid is a substance that ionizes in water to donate a proton. Ooh-wee. Yeah, excuse me about that, guys. Second question, which acid HX or HY is stronger? Give a reason for the answer. HY is stronger than acid HX. Why am I saying that? Because the pH of acid HY is lesser than the pH of acid HX rather. So that's why acid HY is stronger. So HY is stronger. Here, proton donor. Acid HX ionizes in water according to the following equation. Okay, we are given the equation, and this thing simply means that acid HX is a monoprotic acid because it donated or gave away one proton. Okay, we are told that the constant ionization of water value in the reaction is 1.8 multiplied by 10 to the power negative 5 at room temperature. Is the concentration of hydronium ions higher than, lower than, or equal to the concentration of the concentration of HX? Give a reason for your answer. Since my constant ionization, guys, is not greater than 1, it simply means that my acid HX did not ionize completely, which simply means that the concentration of HX is greater than the concentration of the hydronium ions. Are you together? So in this case, we'll simply say that the concentration of the hydronium ions is lower than the concentration of the acid. Okay, let's move on. Learners add 150 cubic centimeters of sodium hydroxide solution of unknown concentration to a 200 cubic centimeters of a 0.03 mole per cubic decimeters of hydrochloric acid solution, as illustrated below. Okay, they find that the pH of the final solution is 2. Assume that the volumes are additive. Since the pH of the solution is 2, it simply means that the acid was in excess. Are you together? So since the acid is in excess, the solution will have a higher concentration of hydronium ions in excess. Okay. Okay, they've given us the balanced equation there. The first question, they want us to calculate the concentration of hydronium ions in the final solution. We are given the pH, right? I know that pH is equal to negative log of the concentration of hydronium ions. For me to find concentration of hydronium ions, I simply need to say 10 to the power negative pH. So this will be 10 to the power negative 2, which is just 0.01 mole per cubic decimeter. together. So the concentration of the OH, of the hydronium ions rather, can either write 1 multiplied by 10 to the power negative 2 mole per cubic decimeter, or if you want to, you can simply write 0.01 moles per cubic decimeter. The power negative 2 simply tells you that there are 2 zeros before 1. Okay, now they want us to calculate the initial concentration of sodium hydroxide. Okay, for us to find the initial concentration of sodium hydroxide, it will be safer for us to find the actual number of moles of the acid that reacted with sodium hydroxide. Remember that it will be easy to find the number of moles of the acid. Why? Because our acid is a standard solution. So before we do that, now let's find out the number of moles of the acid which are in excess. I know that Cn, the acid was the one in excess, right? That means HCl plus water gave us H3O plus Cl minus. So since the ratio here is 1:1, guys, it simply means that the number of moles of the hydrochloric acid in excess is equal to the number of moles of the hydronium ions, which is simply a concentration multiplied by volume. Are you together? Concentration multiplied by volume. In this case, I have 0.01 is my concentration, and my final volume, they said that the volumes are additive, is 200 plus 150, which is simply 350 cubic centimeters. I have to convert that to cubic decimeters, obviously. So I'll simply write 0.35. So I have 0.01 multiplied by 0.35. The number of moles for the acid in excess is 0.035 moles. Are you together? And then the number of moles, the initial number of moles of my acid, number of moles initial for my acid, simply take the concentration multiplied by the volume, right? The concentration, the initial concentration of my acid was 0.03. The volume was 0.2. It was 200 cubic centimeters. Remember that? So the initial number of moles, there was 0.006 moles. So now I can simply calculate the number of moles which were used to neutralize the base. I'll simply say the number of moles which were used to be the number of moles initial minus the number of moles in excess. I have 0.006 minus 0.0035. This will give me 0.00, I believe it's 25 moles. Let me confirm. 0.006 minus 0.0035. Yeah, it's 0.0025 moles. Okay, since, guys, the ratio here is 1:1, so it simply means the number of moles I need to react to neutralize the base, the number of moles of the acid needed to neutralize the base will be equal to the number of moles of the base that are needed to be neutralized by the acid. Are you together? So this thing simply means that I'll just continue here. Let me write in red. The number of moles of my base is equal to the number of moles of the acid that we used to neutralize the base. I'll simply write 0.0025 moles. Are you together? And then for me to calculate the concentration of my base, remember that concentration is number of moles over volume. I want the concentration, the initial concentration of sodium hydroxide. I'll simply take 0.0025 divided by the volume of my base, 150 cubic centimeters. Just write 0.15. Divide by 0.15. I will simply get 0.016666 reoccurring, so I'll simply write 0.17 mole per cubic decimeters. So the initial concentration of my sodium hydroxide is 0.017 moles per cubic decimeter. That's the initial concentration. Yeah, they are tiring, guys, these videos, but I'll keep on doing them for you. Now we are only left with the last video. Okay, just to take you through this last question. Initially, I calculated the number of moles of the acid which were in excess, and then I calculated the initial number of moles of my acid, and then I had to calculate the number of moles which actually reacted with the base, and then I got that to be equal to 0.025 moles. Since the ratio of the acid and the base is 1:1, it simply means that the number of moles needed for the acid will be equal to the number of moles needed from the base. So that means the number of moles for the base will also be 0.0025. And then since I know the number of moles, I know the initial volume of my base, I can simply find the initial concentration, which was 0.017 moles per cubic decimeter. I really hope, guys, that you got helped. Just stay tuned for the last video.